Hi, welcome to my YouTube channel. This is the first video that I've been recording and decided to share some comments about some case uploaded to the ATPDraw website. And I look forward to create more videos for you in different topics using this post-processing tool, powerful tool to calculate electromagnetic transients. Perhaps for the surprise of most people, this software also has the capabilities to calculate thermal transients, which is the topic of interest that I will be discussing today. In this case was originally presented by Professor Kalat, who was the pioneer for implementing the George Anders theory on thermal network methods into ATP or ATPDraw package. Of course, there will be more advanced software or more appropriate software in the context, like finite element method approaches to calculate the thermal rating or the thermal response for any given particular situation of a cable system application. But it is good to illustrate that if you know the equations that describe your phenomena, by using tags and model features from ATPDraw, you're able to represent like every phenomena that could have ever happened in a system. This case is available for every user registered on the ATPDraw website. Is the case number 102, which is 3 single core 10 kilovoltage cables thermal network. I will describe this case right here. As this is described here below, the cables are actually the core cables are copper and have a wire screen that is also copper. The jacket is PVC and the insulation is XLPE. Cables has a particular way of being under the installation, like solidly bonded, regularly transposed, and located in a particular distance below the ground, because this will be an underground directly buried cable installation, as we are seeing here on the icon, which is a custom model. We are sharing models blocks from a custom library to do the thermal network modeling and the transient response on the cables. So for a given size of the conductor, we are representing the electrical equivalent of the thermal network, right? So we have to represent thermal resistivities and thermal insulation of all the layers. This will include the core conductor, the insulation, that according to the theory and the method have to be split into two parts regarding the insulation. And for the cable wire screen, the cable shed, and also for the jacket. Okay, we see here also source, DC source, that is representing the ground temperature surrounding the cables, and we see also a special models block that will represent the losses that are taking part on the core, on the dielectric, and the wire screen. In my humble opinion, as I've been researching and learning, T4 as a thermal resistivity has the most impact on the thermal rating of the cables applications. But I will have to take a brief look on every one of these blocks to explain what they do and what is happening on the system. First, we have to notice that we are using tag sources to inject the output from the models blocks. So that is why these model blocks are within on the very closely to the tag source. I mean to say. So if we look on the core conductor, we will have all the constructive information of the cable. We will, since this case is already prepared, we are seeing values, but we can input and change these values as we require. But this refers to the nominal current, the frequency of operation of the system, the axial separation from the cables or the core conductors, resistivity, correction factor for temperature, and so on. Here are also some factors to take into account: the skin effect and proximity effect. So how is the calculations being done? So if we take a look on the model editor within the edit button, we will see the comments below for every variable, what's the meaning and the dimensional units. And also we will see the implemented approach on the equations, which is based mostly on the ISE standards, which if I am right, Mr. Anders was the chair of those working groups, so the equations are very closely to the ones established on the Anders book. So if you ever read those books, you will be familiar with these equations. And we can see that the output here, the output is the resistance of the core, and we will see why we are doing the output of this variable, and the losses that will be injected. So here we'll see here that for every time step, the models block is taking a temperature of the node, which for this equivalent is a voltage signal, as an input, and then for the same time step doing the losses output to the system. And this is happening for every time step of the simulation. The resistance, we are passing the value to the widescreen because according to the AEC approach standard, there are some loss factors that involves a relationship between the resistance of the cable shed and the core conductor. So it is very useful to pass the value. And to pass the value, we are not using electrical direct connection, but we are referring the value by using same node names. We will see that further on a warning from ATPDraw regarding different nodes that have the same name. And the same thing goes by the core losses, because the core losses are also taking into account to calculate a proportion to estimate the losses on the widescreen. Regarding the dielectric, losses are constants for every time step because they just depends on the voltage level and the frequency of the system. And of course the particular values for a cable installation, that could be tangent delta, for example. So those are constant, but they are present and we are taking into account for every time step. And here we will see half of thermal resistance of the XLPE insulation. You will see that the equation is very simple one, and we are not executing for every time step. We're just doing the initialization and keeping this constant value for every for every time step. Actually, the things that are changing for every time step are the resistance, the Joule effect that it's happening on the core and the wire screen. Something similar happens with all other models blocks, and this includes the T4, right? For T4, we are taking the cable off the center of the cable group, because that is the cable that will be subjected to a more a higher temperature. So that is the, according to AEC standard, that is the temperature that we are taking as a reference value to establish the thermal rating of the configuration or the cable installation. Finally, you select which ground temperature you will have. In this case, the ground temperature is 15 Celsius. So I will run the simulation, and here we have the warning I mentioned before. It's telling us that there are two nodes that have the same nodes, and to check if this is not an error, but actually it does not the case, and we will select all to accept. The program is running, and we can request using block XY the temperatures, and those are voltage signals because of the equivalent of the, or the analogy of the units, right? So here we see the core is the red one and is reaching the rated temperature. So we can confirm that actually that for this given installation, that this current is the nominal current for this particular installation and environment conditions. We can see also the shed temperature on the wire screen, which is lesser than the core conductor. And what is happening here is that from the beginning of the simulation, the cable is loaded. Okay, the AC current is flowing through the core conductor, and then we are seeing here the elevation of the temperature until the thermal transient reach steady state. We have to consider that this is not a cyclic load. This is just constant RMS current. So this behavior is for the thermal transient reaching the steady state value, and at some point the load it is disconnected. So the transient, it's happening again until the cables reach the ambient temperature, which we have established in the beginning of the simulation. This library is available for every ATPDraw user, and we look forward to any feedback and to encourage other users to improve further these model blocks and to develop their own cases for using this powerful software package. I hope that you enjoy my first video, and stay tuned. I will be making more videos. Until then.